Swayam Prabha. Digital India. Educated India.
Good afternoon. This is lecture 15 on the course in Advanced Structural Analysis. We are about to complete this topic of review of Basic Structural Analysis 2. We were looking at displacement methods, and this is covered in part 5 in the book on Basic Structural Analysis. So you will see that the problems that you need to solve fall in 4 broad categories. We finished the first 2. In this session we look at how to solve problems by the displacement method when you have multiple unknown rotations but no unknown translations. That is the 4th type, which we will see later. If you recall, we had done this problem in the last session. This is a continuous beam subjected to relative settlement of 2 supports. We had solved this problem by slope deflection method. Let us see how to solve such problems by the moment distribution method. So the first step is to convert the relative settlements to chord rotations. There are 3 members. You can work out those chord rotations. We have done this in the earlier session. You will notice that the member CD is the one which undergoes an anti-clockwise rotation, so you give a negative sign to that. And what is the degree of kinematic indeterminacy in this problem? 2. I mean, we can reduce it to 2, and the unknown rotations are at B and C. So at B and C we need to do moment distribution. Up till now we have done problems which needed moment distribution only at one location, and you need to do it in one step and you get an exact solution. But now when you have more than one location where you do distribution, it gets to be a little tricky. So let us see how to do that. Your first job is to find fixed end moments. Are there any fixed end moments in this beam subject to support settlements? Not due to external loads, but you need to calculate the additional fixed end moments you get due to these chord rotations, and I hope you remember the formulas. These are easy to work out. In the slope deflection method you do not call them fixed end moments. They come in the slope deflection equations under chord rotation, but they are known quantities. In the moment distribution method you have to explicitly calculate these quantities, and we call them additional fixed end moments, right? And what is the next step in moment distribution method after you get the fixed end moments? Up to this step we have done in the last class. What do we do next? Distribution factors, carryover factors. Shall we do that? You have to find out distribution factors at B and C. Take B. It is 3ei by L, and the i's are different for the 3 elements, and 4ei by L for the middle element, right? So this is straightforward. You do not get clean integers here, so you can find them to as high an order of accuracy as you wish. So here I have given 4 significant figures. So I hope you know how to calculate the distribution factors at joints B and C, which is the ratio of KBA to KBC and KCB to KCD. There is a support at D. And as far as carryover factors are concerned, you do not carry over to the simple supports. So you have only a carryover from B to C and from C to B, and it is equal to half. So this is the distribution table. As you can see from the number of lines I have drawn, you do not get it in one cycle. So how do we do this? First you write down the element numbers, write down the distribution factors, Please note at any joint the sum of all the distribution factors should add up to 1. Then you write down the carryover factors and you write down the fixed end moments. In this case the fixed end moments are caused by the support settlements, right. Now let us also give it a physical meaning. You have this beam in which you have arrested the joints B and C, you have got those fixed end moments, and at the joint B wherever you have arrested it, you have got a moment which you need to release, and when you release it, it is like balancing that moment which you get by distributing the moments to the two ends. So now you have to take minus 100.74 minus 221.87, add it up, you get minus some quantity, and that total you have to distribute to the two ends. So how do you do that? And when you do that, you also have to do a carryover. Then you go to the next joint and do the same thing. Now there are many ways it can be done, and the solution procedure follows a pattern, a technique called relaxation method. You know, it is a numerical way of solving simultaneous equations. If you notice, the superiority of the moment distribution method over the slope deflection method is that we do not calculate theta b and theta c at all, we directly get the moments, whereas in the slope deflection method you calculate theta b, theta c, and you plug those values back into the slope deflection equation. So here there are many ways to do it. The one that we recommend is you first do at this joint. If you have your calculators you can work out, it is pretty straightforward. You add up that total and distribute 0.4497 to the left end and to the right end. So at this stage if you add up all the moments at that joint, it should turn out to be 0, right. Now the suggestion is do not do the carryover now, we will do the carryover later for all the joints in one go. It really does not matter because at the end you have to balance. So this is what we call the first cycle of balancing, and then you move over to the next joint and do exactly the same thing, you will get something, right. It is interesting to note in the second joint you seem to have smaller numbers to distribute in this particular instance, it need not be so for all loading. Now is the time to do the carryover. How do you do the carryover? You can put some arrow marks to help you. 50% of the moment gets carried over plus half. So is this self-explanatory? Everything is clear? Now after you have carried over at the joint B, what is the unbalanced moment? It is plus 10.43. So what should you do now? Again balance it, okay. So that is what you do, and you have to balance 88.77 at joint C. You can do all that in one step. Is it clear? It is a simple thing, you can do it manually very fast. Now what do you do? So this is balance number 2, carry over again, but as you go down the quantities which you carry over are becoming smaller and smaller. So when do you stop?
When
Yeah.
less than some percentage.
When you have done enough number of cycles and you have got tired. In practice you see the power of the moment distribution method is lost if you have to put in a lot of effort to it. So usually in the olden days they stopped with 2 cycles and they said we will live with the error, but today we do not do that. We say that stop till you can tolerate, you accept as an error that unbalanced moment, and that should, it is left to you. If it is very good if you say if it is less than 1% of the maximum moment, some people say 5%. So you can keep on doing this, and we have done 4 cycles here, and you should end with a balancing, because if you leave an unbalanced moment then you will not satisfy equilibrium. So we stop with the 5th cycle of balancing, and then we add up the totals, and when you add up, one way to know whether you have got this right to some extent is that when you add up the 2 moments MBA and MBC, they should add up to 0 because there is no net moment there. Same at CB and CD. So you have got the answers, but there is a little error, but that is a negligible error, right. The error comes from, also in carryover you will have a little rounding off problem, because you have to round off to the first decimal place or so, but we live with that. So this is how you do moment distribution method when you have more than one joint. Is it clear? Here I have got an example of 2 joints. If you have 3 joints, you do parallelly 3, but then today we live in the world of computers and we say it is not worth it. So it is really worth it if you have only one member, one rotation, because then you do it very fast and it is an instant solution, it is 100% accurate. This is not that accurate compared to slope deflection method, and you get exactly the same solution as you get in slope deflection method. Now again I want to go back historically. This is how they did multi-storied frames in the olden days. I mean it is too much to analyze the full frame. So we have this concept of substitute frame. You take any one floor and you assume that there is not much interaction between one floor and the next floor, and you can prove this using Mueller-Brislow's principle, and as long as there is no sway in the frame, you can isolate one frame and assume the columns to be fixed at the top and bottom. So that is what this is, for example, what you can do in a 3-bay multi-storied frame under gravity loads, not under lateral load, because under lateral loads it will sway. Now I made our job easier because I have deliberately chosen a symmetric loading condition, in which case you can take further advantage and cut it in the middle, and what do you put there? Guided fixed support, okay, guided roller support, and you know very well how to analyze this. You have 2 unknown rotations here, theta A and theta B, and you can you need not worry about the delta C because we know the modified stiffness. How do we proceed? Well, first we calculate the fixed end moments. For the column elements there are no fixed end moment because there is no lateral loading on those columns. For the beam elements AB and BC dash, I hope by now you know how to do those calculations. Okay, so let us assume you can calculate these moments correctly. Then you need to find the rotation, the distribution and carryover factors. So let us pause for a while and see how to do this. See, at this joint A you have 3 elements. So you have KAF, KAE and KAB, right. So for KAF it is 4 EI by the height, which is 3.5. For KAE likewise it is 4 EI by 3.5, and for KAB it is 3 EI, 4 EI, but the EI is 3I divided by the span, which is 8. Are you getting it? So you have got 3 members meeting at that joint. So when you make the table you have to arrange it in such a way that you can handle all of them simultaneously, and the same thing you do at joint B. At joint B the only point to remember, here you have 4 elements, is that the stiffness of BC will be EI, and that I is 2I divided by L. Is it clear? So you can work this out. I want you to get the concept clear. So let us say you got this, then it is easy. You make your table, carryover factors. From B to A and A to B it is plus half, and from B to C dash it is minus 1. Clear? Make your table. So let's not do this, let us just see how it is done. It is exactly the same way. You have to arrange your table in such a manner that you can fit in most of the quantities. Nobody does this anymore, so it is a little more of historical importance, but I just wanted you to know that this is how it can be done. Then you can draw your free bodies and bending moment diagram. This is just a demonstration of how moment distribution method was widely used to design buildings till about the 1980s or 1985, very common. Today we do not do it because we got nice softwares which do it automatically for us. What is this structure that you see here? it's called a box culvert. Where is it used? It has many purposes. You can use it for drainage, but let's say you've got a ditch in front of your house and you want to bring your car across. Then instead of putting a slab with a separate foundation and there's a drain going below, you can put a neat box like this, which is very efficient, very stiff, and it's called a box culvert, right? And if you had a concentrated load in that box culvert, say due to your vehicular load coming, then it will be balanced by a soil pressure from below, which is conveniently assumed here to be uniformly distributed. And you could have, what are those triangular pressures you get on the side? Yeah, they come from the soil, and maybe if there is water around there. So it is a self-equilibrating system. This is a self-equilibrating system. You do not talk about supports here, okay? It is self-equilibrating, and you need to analyze this, and you can do it beautifully by either moment distribution or slope deflection method. But there is a symmetry here, isn't it? So why don't we take advantage of that? And when you do that, it will look like that. Divide that load 18 by 2, you get 40, right? Now how many, what's the degree of indeterminacy here? 2, theta A and theta B. So can you find out the fixed end moments? Yes, you know all the formulas. So let's say you know how to do all the fixed end moments. Of course you are more used to beams with loads acting downward. So when the loads are acting upward, you have to stand on your head in your mind and get the directions correct. Plus clockwise is always positive and anti-clockwise is always negative. So that's the only place where you can make a mistake. Okay. Then the distribution factors are easy to calculate. I think by now you are taking advantage of all the modified stiffnesses. Remember, there are only 3 magic numbers to remember. 4 EI by L is very normal, 3 EI by L is if you have a hinge support at the extreme end, and EI by L is when you have a guided fixed support. Is it clear? So you can work out these, and you can work out your carryover factors, do your table. Sorry? Soil pressure when it acts on a retaining wall. Have you gone through a geotechnical course? You are going through. So you will know that take water. If it is water, it is hydrostatic. If it is water, Pascal's law says that the pressure is the same in all directions. If it is soil, it is not the same. So the lateral pressure, it is called the active earth pressure, is less than the vertical pressure. How much less depends on the soil properties. So if you have sandy soil, it is roughly around 1/3. So whatever vertical load you are applying, 1/3 of that pressure goes, so it is a linear variation. That is conveniently assumed. This is Rankine's soil pressure profile. But don't, in structural analysis we say somebody has found out those loads and given it to you, and you know, but in real life you need to work out those loads yourself. So that is where you have to ask those questions, okay. And you get a beautiful symmetric across 2 planes, no, across 1 plane diagram, okay. It is very fast. So the structure looked little formidable when you saw it in the beginning, but now you see it is quite easy to handle, okay. So the idea is for you to know that such things can be done. You have done the assignments, but beyond that we are going to do everything automatically using matrix methods, okay. So it's important to know that this is how many structures were analyzed for many years. Now we go to the 4th category, the toughest, that is when you have sway which you can't get rid of, it is unknown. It is not like a support settlement which is known, the chord rotations are unknown. In some cases you can take advantage of them. We will look at those cases in tomorrow's class. For the time being, let us look at how to deal with this. So if you have a symmetric portal frame with a symmetric loading, what is the deflected shape? Will it be also symmetric? Yes, it will be symmetric. if the loading is slightly eccentric, you have an asymmetric loading, then the question I want to ask you is it going to sway to the left or is it going to sway to the right? What is your hunch? To the right. Did we discuss this earlier? Okay. Now what you need to do to get it intuitively right is keep pushing the load to the extreme length and press it down hard and your mind will tell you which way it is going to move. But you can also give a very beautiful analytical way of explaining why it is going to sway to the right. Let us look at that. Let us say you do a moment distribution of this frame, okay. You have two joints where you have unknown rotations, you can do it, right. Will you get the correct answer? Will you get the correct answer? You will get some moments, but you will have a problem with the answers you get. What is the problem that you get? That is a problem you get in moment distribution method, not with slope deflection method. What is the degree of indeterminacy of such a frame? 2. But there is a sway, so it is 3. So you can't wish away that sway degree of freedom. So the moment distribution method, the way we have learnt it till now, where you have unknown rotations, is not able to handle sway. So if you do by moment distribution method, you are actually doing it for a braced frame, which means without your knowledge you are not letting it sway. That means there is a restraint there, right. So you get something from the distribution table, but the frame you are analyzing is not the original frame, but a frame in which someone has arrested the sway degree of freedom, right, and then your results will be correct for that problem. Now where do you think the moments will be more, in the left column or the right column? Let us take the beam. If it is a fixed beam, where will the fixed end moments be more, left or right? Left. So don't you agree that the it is not fully fixed, it is partially fixed, so those moments get affected, and whatever moment you get in the beam end will be passed on equal and opposite to the column end. So don't you realize that the column on the left side is likely to have more bending moment at the top than on the right side, right, and the moment at the bottom is 0 because it is a hinge at the bottom. Now if you, will you have a horizontal force at the bottom? Yes. What will be the value of that force? It will be the moment at the top of the column divided by the height of the column. So you will get two horizontal forces, which one will be more or will they be equal? Why do they have to be equal?
And opposite.
Yes, right. So to satisfy equilibrium, where will that force have to go?
That hinge.
That artificial support that you,
artificial support.
that is the key to it, you are right. So you are, if you do moment distribution method, you won't be able to satisfy equilibrium because your horizontal forces are you will find you will need a net horizontal force the way I have shown you, and then you have to do another analysis which is called a pure sway analysis, where you have a horizontal load acting in. So this is the problem with moment distribution method, that is you need to do two distributions, one with the sway arrested, in the other you have to figure out how much that sway, then do that analysis. So it is not worth it, and so we won't follow moment distribution method beyond this point. We will say if you have such problems you can do it, but we have grown up and we do not do it that way, okay. And here you can clearly see why it is going to sway to the right, because the net load is going to act in that direction. You have to reverse the load acting on your artificial restraint. This is a beautiful powerful left brain understanding of why the sway is always to the right, okay. Now let us say how to deal with sway. I have suggested that do not deal directly with translation, always deal with chord rotation because they are much easier to deal with. So you will have sway degrees of freedom in a frame like this. To figure out how many sway degrees of freedom you need to have, you conveniently put hinges at all the junctions and let it sway like a mechanism, and then you will find there is only one unknown degree of freedom here, that is delta. Is it clear? So the other way to do it is, at every joint in a plane frame you have two translational degrees of freedom, any two orthogonal directions you can take, vertical and horizontal. So you have at A and D both are arrested, so you have 4 potential degrees of freedom at B and C, agreed? 4 translational degrees of freedom. But if you assume members to be actually rigid, you are bringing in as many constraints as there are members. So you have 3 constraints because 3 lengths remain unchanged, the length of AB, the length of BC and the length of CD. So that is a clever way of figuring out how many independent sway degrees of freedom you have. 4 potential translation degrees of freedom, 3 constraining equations because of the length, 4 minus 3 is equal to 1, got it? And you can choose any one, in this case delta. And then you work out your chord rotations. If delta is to the right positive, then the chord rotation phi AB is delta by h and CD is also delta by h. What happens if your roof is tilted? Okay, it is called a bent portal frame. Then also you have 3 members, 4 potential degrees of freedom, 4 minus 3 1. Then also you have only one unknown and its delta, both will move parallelly, both the columns will move parallelly as shown here. And what is interesting is the beam does not have any chord rotation, whether the beam is horizontal or inclined, there is no chord rotation. So you will have sway, you have chord rotation only in the vertical elements, and the chord rotation in AB is delta by h1, the chord rotation in CD is delta by h2, got it? So we are going to increase the complexity now. What you do when you have a frame like this, we will solve this problem tomorrow, when do you encounter frames like this? Well, you have got a house in a hilly site, Banjara Hills in Hyderabad maybe, and you enter from the first floor here and the ground floor there, and your architect wants a fancy design with inclined walls, and so you can have a frame like that, your foundations are at 2 different levels, right? Then also you should remember, even though it looks complicated, and this is a very interesting problem, you do not need to solve it, but at least conceptually you should know how to solve it. You still have only one sway degree of freedom. Why? Because 4 potential translations at B and C, 3 members, 3 constraining equations, 4 minus 3 1. You can still choose delta, but now your beam is going to have a chord rotation, because if you play with it like as you play with the mechano set, it is a mechanism. If you play with it, if these are rigid members, it will take a shape like this, agreed? And chord rotation for AB is simple, it is phi AB is delta by h1. For CD also it is simple, it is delta by h2, but it is a little tricky when you calculate. You can use trigonometry and calculate, and that is the formula that you get. I would like you to, these books are available for you, but that is how you do it. This is how it was done in the olden days. In slope deflection method you do not have to worry at all about these things, you can do it directly. In the matrix method also it is done directly. If you have a pitch portal frame, you can similarly work out those equations, do not worry too much about it. Normally our buildings do not look that funny, you do not have inclined columns, you do not have inclined beams, You have frames which are called reticulated frames, made up of rectangles, where your life is made easier. And if you say axial deformations are negligible, then you have only one rotational unknown at every joint and one sway degree in every floor, right. Why only one sway degree in every floor? Because all the joints in that floor will move like a rigid body, okay. And there are serviceability limitations in a tall building. The maximum drift in the building should be limited, okay. Usually it is height by 500 under lateral loads, okay. So can you analyze a frame like this? Exact solution? Yes, that is the idea. We want to be able to handle any structure, any skeletal structure of any shape subject to any loading, including indirect loading, okay. That is the objective of structural analysis. Okay, now in slope deflection equations, till now we were conveniently having only rotational unknowns, and the moment equilibrium equations were MBA plus MBC is equal to 0 kind of equations. Now you have a translational unknown, so a moment equation is not going to work here, so you need a force equilibrium equation. It is called a shear equilibrium equation. Let us demonstrate that. Let us take this example, okay. This example where you have a portal frame with an asymmetric load, unsymmetric load, right. First identify what are your unknown displacements, theta b, theta c, and you can call it just delta, or you can call it delta bc, because every point in that beam is going to translate by the same delta. So theta b, theta c, delta bc. Fixed end moments, well, your columns do not have any fixed end moments, but your beam does, and you can easily calculate that, right. You can calculate a fixed end moments in the beam, right, minus W a b squared by L squared plus W a squared b by L squared, fine. Now what do we do next? Slope deflection method. What do we do next? You have to write down the slope deflection equations, okay. Chord rotations are clear here, right. So what will they look like? Will you try it? Write down the slope deflection equations for the three members AB, BC and CD. So how many equations do you need to write down? 6 equations, and you can write them mechanically. Of the 6 equations, in the 6 equations you have to put them in terms of 3 unknowns. What are the 3 unknowns? Well, instead of phi you say delta, delta by 4 is phi, right, okay. So let us demonstrate for AB. Do you agree with this? MAB is MFAB plus 4 EI by L of theta A is gone because theta A is 0. So you are left with 2 EI by L of theta B minus 6 EI by L into phi. Phi is delta by 4. Is it clear? Likewise, you can write for MBA. MBA will be MFBA plus 4 EI by L theta B minus 6 EI by L into phi, right. Theta C, where is it? It is outside AB, so do not worry, right. Theta C is not, same thing in a continuous beam, right. You had theta B, theta C. When you were dealing with this beam, C was far away, so you do not have to worry about it. Is it clear? If you open them out and make it look like a continuous beam, you are writing down same equations. Is there any doubt on this? And in the same manner you can write for BC. In BC will there be any sway? Any chord rotation? No. So for BC it is a straightforward thing. Fixed end moment you can write down in simple 4 EI by L theta B and 2 EI by L theta c. Is it clear? For MBA, for MBC and for MCB, straightforward. And for MCD and DC, they will look similar to MAB and MBA, right. So actually you have to just copy those equations. Only thing, your theta b gets replaced now by theta c, but you have to put the right theta at the right place. I hope you now understand that slope deflection equations are a blind method of doing it. You do not have to worry about anything, you get this. Now what is the next step? Write down the, so you need 3 equations, 2 of them are very easy. So corresponding to, okay, I can summarize and write it nicely in this matrix form. Okay, so you look carefully here. These are my 6 moments, right, 3 pairs, 3 elements. These are my fixed end moments, only the beam has fixed end moments, the columns do not have fixed end moments. These are my coefficients related to EI theta b, EI delta c and EI delta bc, which comes from either 4 EI by L or 2 EI by L or 6 EI by L squared, right. And if somehow I get the answers for theta, EI theta b, EI theta c, EI delta, then I just plug it in, I get the final answers, very simple. Is it clear? Now the big question is, how do I get those 3 equations? 2 of them are straightforward, we have done it in continuous beams. There is no net moment at B, no net moment at C. You pick up the second and third rows and just add it up, you will get 2 equations. Where do you get the third equation? Please tell me how to write it. How to write the third equation? The clue is you have to write it in terms of these moments. How will you write it?
MA equal to MAB equal to MB.
And difference in the
You tell me, this is your structure. Tell me what to do. Vertical reaction. You will be able to write the reaction in terms of MBC and MCB.
Sir, MAB is
How
equal
does that
to
help you?
MDC. No, sir.
I will give you a clue. No,
Sir,
I'll give you
MAB
a
is
clue.
equal to MDC.
Huh?
MAB is equal to MDC.
Who told you?
Horizontal force at B and C. Those
Horizontal force is different from moment.
that into this
I will
gives
give
me-
you a clue. See, you wrote MBA plus MBC equals 0 because there is a B common there, because theta B was the corresponding unknown rotation. Now you have delta BC, you have a sway degree of freedom, you have to write a force equilibrium equation, right, not a moment equilibrium equation. Which force? What equilibrium?
The shear force in column A.
The shear force in column AB. Is it a constant shear force?
Resultant.
Is it a constant shear force? Is it a constant shear? Yes.
Yes, sir.
Because you have a column, if you take the free body of the column, you have a moment only at the top and the bottom, there is no intermediate load. And let us say they are clockwise positives, you have MBA and you have MAB, so your shear force is?
Difference by
Well, they are both positive, so where is the difference?
2 MBA by
You
4.
add them, MAB plus MBA divided by H will give you a shear force. Well, to make your life easier, why don't you look at it as horizontal reaction at A and D? What should those 2 reactions add up to? That's the easiest thing you can do. So don't break your head too much over it, that's all you need to do. Horizontal reaction at A and D should add up to 0, and for the sign convention we have assumed MAB plus MBA divided by 4 clockwise, where is that reaction pointing, from left to right or right to left? This is so for equilibrium this will point this way and this will point this way. This is what we call HA. and it will be right, and this will be equal to this, and wherever you cut a section the shear force is constant. What happens if you have, instead of AB you have DC and CD? Well, the only change is this A becomes D and you get so this is the thinking you need to do. And now you've got expressions of MAB, MBA from your slope deflection equation, plug it into that equation and you've got 3 equations. So George Maney discovered this way back, 100 years back, powerful method. You get, actually the last equation you have to play a little with, play a bit with it to get the symmetry in that matrix, okay. Actually they don't turn out to be the way it is I have shown you, because there is a minus sign, you have to multiply that row with -1, you will get the symmetry, okay. Now what does this matrix look like? What is that matrix? Displacement methods are stiffness methods, not flexibility methods. That matrix is a property of the structure. What is that matrix called? Well, it is related to the stiffness matrix, and the beautiful part about this is the vector that you get here is caused by the loads. The left side is completely a property of the structure. You change the loads, only this will change, this will not change. And so we will see how you can generate that stiffness matrix from first principles. I am stepping ahead into matrix methods, but I want us to go through that exercise. We got this blindly by just applying equilibrium equations, right, but with our eyes open can we generate this matrix? Let us do that, because then you have a real understanding of the physics behind the mathematics, okay. So you can solve these equations, and nowadays you have calculators which do it just by pressing some buttons, so I won't waste time. You will get these answers, okay, and then what should you do? Plug them back into the slope deflection equations, you have got the answers. So after you have got the end moments, what should you do? You draw free body diagrams. I hope you know how to do that. Draw the free body diagrams. Clockwise moment, put clockwise. Negative sign, put anti-clockwise, and then everything should match, all the equilibrium should be satisfied. You can now find the vertical reactions in the beam and the horizontal reactions in the column, and you will find that there is perfect equilibrium, everything is balanced, you have got the exact solution. Powerful method, agreed? Then you can draw the bending moment diagram, it will look like that. So you are not afraid of sway, you know how to deal with sway, okay. But if you have multiple sway degrees of freedom, you have to do it a little more carefully. Now I want us to go through this small exercise of generating the stiffness matrix of this frame from first principle. Shall we give it a try? Okay, you love it, it is simple. How many degrees of freedom are there? 3. Shall we number them? 1, 2, 3. Theta B is our first degree of freedom, theta C is our second degree of freedom, delta BC is our third degree of freedom, okay. To generate the stiffness matrix of this, what should I do? What is the size of what is the order of the matrix? 3 by 3. What should I do? From first principle.
Give a unit displacement at that location.
Give a unit displacement. Let us say I want to fill the first
find
row.
The forces at that
first column of the stiffness matrix. What should I do? First I should arrest everything.
Yes, sir. Rotate only at
and then I should allow only
unit displacement
one displacement at a time. Which one?
First one.
So shall we call it D1? D1 should be 1, D2 should be 0. Can you sketch the deflected shape of such a frame? Do it. Sketch the deflected shape. We are trying to find the first column So, to fill this column we need to put, right, draw a sketch. What will it look like? It should look like this, right? It should look like this. Only a unit rotation at B, no translation, no rotation at C, right? Okay. Can you draw the next one? Can you draw the sketch that you need to do for this one? What will it look like? Okay, let's look at this. What is the physical meaning of K11?
Displacement at 1 cause it due to sorry.
So
Force at 1.
when you hear of stiffness, you are reminded of a spring constant, right? So it's a stiffness. So a spring stiffness is force per unit deflection. Here you have two coordinates. So it's a force at the coordinate 1 caused by a unit displacement at the coordinate j with all other coordinates arrested. So here only theta 1, only d1 is there, and so one way to do it is you remove that restraint and you deliberately give an external moment. That moment you need to apply to make the joint rotate by a unit angle is K11, and the reaction that develops at the other artificially fixed end at B is K21, and the reaction that is developed in the direction of the coordinate you have identified in the translation degree of freedom is called K31. Can you calculate these quantities? Do it. Or maybe let's draw this also, the next case which is similar. Your job now is to calculate K11. What is K11? Yes?
80A by L.
No, wrong.
Theta equal to 109.
Okay, let's do it slowly. It is going to be 4 EI by, what is L? 4 EI by 4 plus
4 into 2
6EA by
okay.
4EA.
Okay, these are the other notations. Agreed? Right? Now we need not do, this is equal to what from the other figure? K11 will be equal to K22, is it not? So we need not spend more time on that. K11 and K22 will be identical. Can you find out K12 or K21? K21 is how much? It's a carryover moment you get, no?
2 by 3 EI. 2 by 3 EI.
Which one?
2 by 3 EI.
Wait 1 minute. You have a problem with this addition?
4 EI by 4 plus 4 EI. That's 1 plus 4 by 3. 7 by 3.
7 by 3, that's right. Yeah, that's right. It's 7 by 3. You are right. Well caught. 7 by 3. Agreed. 7 by 3. Okay, this one? This is correct?
Yes, sir.
Okay. It's 7 by 3, not 8 by 3. You are right. Good. This is equal to K12, so there itself you see the symmetry in the matrix. What is left over here? K31. Can you find out what K31 is? That's a clue. That's a clue. That's a clue. So you had here, if you take that column, you had how much? 4 EI by 4. And what do you get here? 2 EI by 4. And this will give you shears which are going to be equal to 6 EI by 4 squared. And so if you take that frame in which you arrested this degree of freedom and arrested this degree of freedom and you applied K11, equilibrium suggests that you will definitely get a horizontal reaction here which is equal to this quantity, and you don't get anything here because this doesn't bend. So the reaction you get here will be equal to how much? No, minus, because they should add up to 0. So minus how much?
6 EI by 16.
6 EI by 16 works out to
3 EI by 8.
3 EI by. That's it. This is the physical approach. Now it's easy. Now it's easy. Okay, right? And this will be equal to K32 in the second figure. So we've got the first two columns very easily. Last column. Can you draw the sketch?
Infinite rigidity of.
That's
infinite
right.
rigidity of
It's like a rigid beam. This is how it's going to move. Point of contraflexure will be in the mid height of every column. So what will it look like? Can you calculate? Can you calculate K13 and K23? It's like settlement of supports. It's like settlement of supports. It's a chord rotation. So what's the moment that you get? K13 and K23?
K33 into L.
6 EI by?
4.
Sir, K33 into L by 2.
Into 1 by 4. Because your chord rotation is 1 by 4. So remember this. Remember this. If I have a settlement of supports problem and this is delta, this is the shape that you get. Clockwise chord rotation will give you anti-clockwise end moments. What are these moments? Well, 6, now don't talk about 5, it will come to 6 EI L squared by delta, because delta by L is 5. Don't make mistakes like that, you will lose everything. Okay, so that's easy now. You got it? And there is a minus sign. Clockwise chord rotation will give you anti-clockwise end moments. Got it? So you got K13, you got K23, you got everything in this matrix except this last fellow. What is K33? Will it be positive or negative? Do you need to think to answer this? All the diagonal elements have to be positive. Why?
Displacement caused it.
Well, what does it mean? I am pushing it to the right. Obviously it's going to deflect to the right. If I kick a football to the front, it's not going to come back. You understand? So that's what all the diagonal elements are doing. I am pushing it in the same direction as identified positive degree of freedom. So it has to be positive. Don't break your head over it. Okay, the off diagonal elements can be negative or positive. Diagonal elements will always be positive. How much will it be? So what are the shears you get here? This is 6 EI by L squared, this is 6 EI by L squared. The shear will be? What will, tell me the value.
3 delta by L cube.
3 I delta by.
Where did you get 3 from?
3 delta by.
Come on, where do you get 3 from?
By 2, sir.
What by 2?
Moment plus.
Take this free body. What will be this shear? What did we do here? Say this plus this divided by that.
6 6EI delta.
If you are an accountant, your bank balance will have reduced by 1/4 by now if you play games like this, right. So it's not 3, it's 12, 1/4. The answer you've given is 1/4 the correct answer, isn't it? This moment plus this moment divided by that span. 12 VI, it's right in front of you, by L cubed. That's interesting. So what's the answer? What is K33? What is K33? Give me the answer, final answer. Is it 12 VI by 4 cubed? No, wrong, answer is wrong. No. What a pity. Twice, because there are 2 columns. The 2 columns at the bottom, you have 2 reactions, they should all add up to that applied force. So into 2. Don't make mistakes like this. So physical approach is for bright students who are alert, who know how to satisfy equilibrium, but it's wonderful, is it not? So if you do that, apart from that small mistake of 8 by 3 which should be 7 by 3, you get the same matrix which we got in the blind manner, right. We did it the blind way and we got the same answer. As I said, don't attempt this by moment distribution, but if by chance you did it, then you get the same fixed end moments, you get the distribution factors, you draw the table, you get some values, but the problem is you will not satisfy equilibrium, and you can check it out. You will find that the horizontal reactions don't match. There is a balance and you need to analyze the frame for that lateral load. So let us not do moment distribution method when there is sway. I will conclude by dealing with one last problem of pure sway. You have this frame subject to pure sway, okay. How do you solve this problem? Are there any fixed end moments? No fixed end moments. Deflected shape will look like that. Remember we did an approximate analysis when we did portal method, cantilever method. We don't do anything approximate now, we do exact, the exact solution. So same 3 unknown displacements. I won't waste time writing down slope deflection equations because they are the same as in the previous problem with one additional advantage. What's the advantage? No fixed end moments, right. This pure sway that's going to the node, it's not going in between any member. Then what about your equilibrium equations? Same, except in that last equation when you put sigma fx equal to 0, you have to add the lateral load which was not there in the earlier problem and do it properly. Put plus 50 on the left hand side of the equation and not on the right hand side, because you will get totally wrong results otherwise. Clear? Then you get the same stiffness. In fact, if you do stiffness method, you can use this, you don't have to do slope deflection method. F1 is 0, F2 is 0, F3 is 50, right. So you can do it this way also. So now you see this is the stiffness method which we are going to do soon. Solve it, plug it into the back into the slope deflection equations, you get this answer which we got. Now look at this problem. I am going to raise a question and we will stop this class. There is something nice about this bending moment diagram. What do you call such a figure? It's not symmetric, it is anti-symmetric. So that gives you a clue. It's anti-symmetric and the moment at the middle of the beam is 0. So maybe we could have taken advantage of this anti-symmetry. How do we take advantage of it? You can do this, symmetry plus anti-symmetry, and when you cut it in the middle, because that is where your moment is 0, you can replace your original structure with this structure. This structure does not have any bending, pure axial compression in this member, only this will bend, and now it's left to you, you can either choose the left one or the right one, so your problem has become much less complicated. How many unknowns do you have there? Theta b. Why? You can ignore sway, you can, because it's a cantilever action. We've done a problem earlier like this, so life is easy. You have to just take out that. Theta b is your unknown, right? We will look at this in the next class, but this is a beautiful shortcut method. This is what we will explore in the next class, and this is what you've got in your assignment, the last problem, but you've got 2 floors. Thank you.